This presentation provides an overview for confidence interval. We will also focus on finding confidence interval for population mean when the population standard deviation sigma is given to us. A confidence interval estimate for a population parameter provides a range of plausible values for the population parameter. The confidence interval estimate is point estimate plus minus the margin of error, also known as MOE. The center of this interval is at the point estimate of the population parameter. Its width is determined by margin of error. The purpose of having a confidence interval is to provide information about how close this particular point estimate is to the value of a population parameter. Confidence level is a probability that represents how confident we are with the interval estimate. The definition or interpretation of confidence interval is the following. If the 95% confidence interval for population mean salary is $50,000 to $60,000, it means that there is a 95% probability for the true population mean salary to be anywhere between $50,000 to $60,000. An alternative definition of the 95% confidence interval is that we are 95% confident that the true population mean salary is between $50,000 and $60,000. Some commonly used confidence levels are 90%, 95%, and 99%, but you could have any confidence levels anywhere between 0 and 1. For the population mean, when the population standard deviation sigma is known, the confidence interval will have the following structure. The point estimate of the population mean is the sample mean, x bar. The margin of error is a product of two things, a z-multiplier and the standard error of the sample mean. The z-multiplier is a z-score from the z-table and depends on the confidence level. The sample mean and the standard error are the same as what we discussed earlier on. I will explain how to find a z-multiplier on the next slide. I will use the 95% confidence level as one example here. First, we will draw a bell curve to represent the standard normal distribution, also known as the z-curve. The middle portion represents 95%. That's the shaded region here. Using the total area under the curve to be 100%, the two corners should add up to 5%. That means each corner is 2.5%. The z-multiplier is just a positive z-score with a corresponding upper-tailed area of 2.5%. From the z-table, that is found to be 1.96. To find a z-multiplier for 99% confidence level, I could also find a z-score with a corresponding upper-tailed area of 0.5% using the z-table. Since there are two z-scores with corresponding upper-tailed probabilities that are equally far away from 0.5%, I would use the average of these two z-scores, and that's going to give me 2.575. The z-multiplier for 90% confidence level is positive 1.645. For these three commonly used confidence levels, when the population standard deviation is given, the z-multipliers are these three numbers found on the z-tables. I would recommend you to memorize these three numbers so you don't have to look up the z-table every time you work on a confidence level estimation problem. We would work on the same example that we have discussed earlier. Now we have a part D that asks for 95% confidence interval for the population average. To find a confidence interval, we would use the expression we just learned, point estimate plus minus the margin of error. Point estimate 75, and the margin of error is the product of a z-multiplier and a standard error. The z-multiplier for 95% confidence level is just 1.96, and the standard error can be found by plugging in the population standard deviation and the sample size into the formula. Let's look at the confidence interval we just estimated. This interval indicates that there is a 95% probability that true population average cars sold annually by used car salesperson is anywhere between 72.06 and 77.94. For 99%, 90% confidence intervals, The estimation procedures are fairly similar. Everything is the same except the z-multipliers. Instead of using 1.96 for 95%, we would have to use 2.575 for 99% and 1.645 for 90% instead. Let's take a look at the relationship between the confidence level and the margin of error. The margin of error is the product of the z-multiplier and the standard error. When confidence level increases, say from 90% to 99%, the z-multiplier also increases. Consequently, the margin of error also increases. You may recall that the margin of error directly determines how wide this interval is. This implies that to achieve a higher confidence level, we would have to have a wider confidence interval. This slide explores the relationship between the sample size and the margin of error. The sample size determines the standard error, which affects the margin of error. When the sample size increases from 9 to 250 and the standard error drops, the margin of error also drops. This implies that when our sample size increases, we can have a narrower interval to achieve the same confidence level. In this example, we would discuss how to solve one type of problems asking for sample size. I would call this type of problems as sample size problems. From previous calculations, we know that at a 95% confidence level, a sample size of 9 would give us an MOE of 9.8. A sample size of 100 would give us an MOE of 2.94. Even when the sample size is 250, the MOE is still 1.86. If we want to reduce the MOE to only 1.5, how large of a sample is necessary? To solve this problem, we can use the expression for MOE. On the left-hand side of the equation is MOE, that is equal to 1.5, that is given in the question. On the right-hand side of the equation, it is z-multiplier multiplied by population standard deviation and divided by square root of sample size. That would be 1.96 times 15 and divided by square root of n. Now we want to solve for n. With some cross multiplication, n is found to be 384.16. We would have to round up for the sample size problems. Because if we only use sample of 384 salesperson, the margin of error would still be slightly larger than 1.5. That is not what we wanted. So we would have to sample 385 salesperson instead. I have also summarized the formula for sample size problem here. Sample size is the squared of a multiplier multiplied by population standard deviation divided by desired MOE. This example is fairly similar to the one we just discussed earlier on. The answers to this example can be found on our course page. Again, I have summarized the formula for sample size problems here. Occasionally, the population standard deviation is not given, but the range of the data values is given. We can approximate the population standard deviation using range over 4. The example on the next slide would make use of this relationship to solve for sample size. For this example, we want to estimate the sample mean to be within 1 day. That is a different way of saying that we want to reduce the margin of error to 1. Because you may remember that the confidence interval is a point estimate plus minus the margin of error. Again, this is a sample size problem because we are interested in finding the sample size that is necessary to reduce the margin of error to 1. We would have to use the formula we just learned. If we look closely, the population standard deviation is not given anywhere in this question. Because the ages of items are between 30 and 130 days, we can find a range to be the difference between 130 and 30. That is 100. Using this piece of information, we can estimate the population standard deviation to be 100 over 4, that is 25. The rest of the calculations are similar to what we have done before. The answers again can be found on our course page.